Hi everybody, my name is Cameron and today we're going to be looking at electromagnetism, specifically magnets, motors, transformers, alternators and dynamos. Okay, so magnets are objects that produce magnetic fields. Okay, so what is a magnetic field? It's the area around a magnet, okay, that different objects will experience an attraction or repulsion force in. Okay, so they consist of two poles. We know it as north and south. The field lines represent the magnetic field. They're always going to be drawn from north to south. Okay, so magnetic fields go from the north pole to the south pole, and like poles, we know repel each other. So north and north are going to repel. Unlike poles, like north and south, are going to attract one another. Okay, when it comes to magnets, we can have a permanent magnet or an induced magnet. A permanent magnet is something that is a magnet uh, constantly. Okay, this can form naturally from something called magnetite. Okay, so you can dig up some rocks that are naturally magnetic and they stay magnetic. Okay, we can also induce or create magnets that will stay as permanent magnets, but it depends on the type of material it's made out of as to how long. Okay, then we have induced magnets. Now, an induced magnet is going to be something that is electrically charged, okay, to become a magnet. Okay, and some of the metals that we'll use for that are like iron, cobalt, nickel, and steel. Okay, because they're going to lose that magnetic attraction relatively quickly. Okay, and magnetic flux density, all this is talking about is those lines. So other than showing us direction, these lines are also going to tell us how strong the magnetic field is at a certain point. So the closer we get to the source, the more lines we're going to see around that area. As we get further out, the lines are going to become less and less, okay, as they themselves are have a greater distance between them. As we can see here, these magnetic field lines have like poles. Okay, the null point is where there is no magnetic force experienced. Okay, and the lines are going to be repelling from one another. As we see here, from north to south, from north to south. Okay, that should be the other way around. And then as we see here, unlike poles are going to attract, so it's still going to go from north to south and north to south. Okay, north to south. Okay, so as we know, our Earth is like one big giant magnet. It has a north pole and it has a south pole. Okay, but the north pole and the south pole aren't necessarily found in the Arctic at the top and Antarctic at the bottom. Okay, they are slightly off, and each year they are going to be moving. Okay, away from geographic north and south. And when it comes to a compass, okay, it might point north, but it's actually the south side of that compass's magnet that is pointing towards the North Pole. Okay. Okay, when it comes to, I guess you could say, sort of induced magnetism in wires, okay, it happens when there is a current flowing through the wire. This magnetic field will be created. Okay, and how we can calculate the direction, or not calculate, but find the direction of the magnetic field as well as the direction of the current. Okay, we use the right hand grip rule. Okay, so if our current is going upwards, okay, or towards us, we use this dot in the center, kind of like an arrow coming towards you. Okay, and then you know that the current is going to be going in this anti-clockwise direction. Okay, do it yourself. I don't know if it's going to reflect badly on the camera, but if the current is going away from us, okay, we use these X shaped like the feathers of an arrow going away from you. Okay, and if it's going away, then it's going in a clockwise direction. Okay, if it's going to the left, then we know the current is going over. If it's going to the right, it's coming over towards us. Okay, stick your hand out, do it, try see which direction you think the current might be going, and then which direction the magnetic flux is. So here's a better example that you can see. As the current is going in this case, around like that, we would put our fingers showing the direction of the current turning in the wire. and therefore we know which way is going to be north and which way is going to be south. So your thumb will be pointing towards north. Ways of so what we call this idea of a current moving through a wire that is wrapped around a central pole, creating a magnet, is called a solenoid. Okay, and these solenoids can be used to control induced magnets. Okay, and how would we change the magnetism of a solenoid? We would either increase the current, so make more electricity go through it, or we can increase the amount of turns around our central core. That would also increase the magnetic field generated. So these electromagnets again are induced magnets. Okay, it means that they can be turned on and off at a whim. And when we use this, sometimes for cranes, okay, that pick up metals, but they don't want the metal to stay there, and then they turn it off, and the metal gets released. Okay, another one would be a lot of security doors. Okay, so they have an induced magnet, and then as soon as the power cuts, as in your finger scanner or your card machine turns the switch off, then the magnet will disengage, allow you to open the door. But as soon as the door closes again, the magnet engages and the door is shut. So, electromagnetic motors are kind of like using a solenoid to make something move. Okay, now imagine you put a solenoid that is these northern facing poles, okay, into another magnet. This is basically how motors are going to work. Okay, so we're going to have this force applied, okay, or this current turning into a force. And the calculation we're going to use is force is equal to the magnetic field, okay, which is B, multiplied by the current, multiplied by the length, okay. And so basically force equals BIL. The field is going to be proportional to the current, okay, obviously, because as you increase the current and the length of the wire, you're going to be increasing the strength of the magnetic field current. We got that in solenoid, right? And the spin of the motor can be reversed if the current is reversed. So if we change our current going in this direction around, okay, all of a sudden going in the opposite direction, then the electromagnetic field line gets reversed and the motor will reverse. Okay, the magnetic field strength is also going to be measured in magnetic flux density, as we said, how closely packed those lines are to one another. Okay, and this is when we're going to use the left-hand motor rule, okay, to figure out exactly which direction usually it's going to move. Okay, so how we do that, we take our left hand, okay. Our pointing finger is going to be for the field lines. Okay, so in this case of this picture, the field lines would be going north to south. Okay, yes, north to south. And then our middle finger is going to be for our current. Okay, so our middle finger is going to, you pick a point on the wire really, and you're going to move it. So let's say it's on the right hand side there. Okay, so our field line, our current moving upwards, okay, and therefore this side is going to be moving downwards. Okay, if we go from the left hand side of this solenoid now, our field line's still going left to right, okay, but our current is moving downwards, therefore it's going to be moving upwards. Okay, the thrust is going to be upwards. Now, generators and transformers are a bit different. Okay, how generators work, they're going to use a magnet to induce a flow of electrons through a wire, thus producing electricity. Okay, transformers, on the other hand, are going to alter the amount of potential, the potential difference between two wires. So where would we see this? Okay, imagine for a generator, we use a wind turbine. Okay, what's going to happen is that wind turbine spinning is going to have magnets inside of it, and those magnets are going to induce a current. They're going to make the electrons in the wire move and generate electricity. Okay, sometimes they also use this with brakes. They put brakes on it, well, always really. They put brakes on it, and those brakes are going to cause lots of these little wheels to turn and spin. Okay, and that's going to generate electricity. Whereas a transformer, we can use a step up or a step down transformer. Okay, so what this will be for is when we are generating electricity now on a large scale, we don't want a power plant's electricity to be in our wall plug. Okay, if some kid sticks a fork in there or something, it's going to be disastrous. Okay, or if an electrician does something wrong, it's going to kill him. So what we have to do is we have to step that power down. How we do that is by having many wires wrapped around one side and a few wrapped around the other side. Okay, so the outgoing voltage is going to be decreased and the current is going to increase. You can also have a step up transformer, okay, which is when they need to transport it long distances. Okay. Okay, next we get to alternators. A bit of a weird one. Okay, but alternators are going to consist of a rotating coil within a magnetic field. Okay, so this is going to induce a potential difference between 2 points of this wire. Okay, as it cuts through the magnetic field lines. But the thing is, it's going to produce an alternating current, meaning that the current is going to go positive, then negative, then positive, then negative, as the coil, using your left hand rule, okay, is going to have a change in current, be it on this side, or it turns around and now the current is moving in the opposite direction. Okay, so therefore the current is going to be changing. Okay, so when it rotates upwards, potential difference meter shows a positive voltage, and when it rotates downwards, the potential difference meter shows a negative voltage. The current in the circuit changes direction repeatedly due to this induced alternating potential difference, obviously. And the higher frequency, the higher the peak. Okay, so this can obviously then be changed by increasing the number of turns on our coil, as well as using a stronger magnet, okay, and moving the wire faster. Okay, that would then increase the induced potential difference of this alternator. And we can see there the induced potential difference is highest when the plane of the coil is parallel to the magnetic field lines, and 0 when it is perpendicular. Okay, so when it's perpendicular, it's not cutting through as many lines, but as soon as it goes parallel, that's when we get our peaks, because as it's moving, it's cutting through the most magnetic field lines, okay, as it's getting closer to those sources. And unlike a direct current generator, which uses a split ring commutator, the alternator has a naturally produced AC current with varying potential difference due to the fact that it is turning inside of these magnets and cutting lines in directions, okay, which is going to change the current back and forth, back and forth. As I said earlier, if you were to take a motor, not an alternator, a motor now, okay, and induce a current, those magnets would spin around the wire, okay. If you were to change the current, okay, so switch the positive and the negative around, it would turn in the opposite direction. And that's basically what's happening here. But instead of switching the current using, a battery or something, it's switching the current because the ring, the alternator itself, is what's spinning around these magnets. So a dynamo is kind of in the similar, or it kind of works in the same way as a alternator. Okay, the only difference is this is direct current, so it doesn't alternate. Okay, it stays, as we can see here in the graph, sort of positive. Okay, it goes to 0, but then it goes back to positive. And how it does this is by using a split ring commutator. You can go search it online, but all you have to know about a split ring commutator is that it's going to change the currents every half turn, okay, to keep it going in one direction. Okay. So the potential difference induced is going to be highest when the coil again is parallel to the magnetic field lines, and then 0 when it's perpendicular. Okay, so it's a bit different to the alternator in that sense. And the faster rotation of the coil increases the frequency and the strength, as well as how many coils we have. Okay, this is going to be used in microphones and speakers. The induced potential difference does not reverse in the direction, unlike an alternator. Okay, so it varies from 0 to max. And yeah, my name's Cameron, and this has been Electromagnetism. I will see you in the next lesson.